Hi, my name is Andrew Brown, and today I'll be presenting on the history of cartography. Have you ever been to an amusement park and gotten lost? What about at Walmart or Kroger while grocery shopping? What about having gone into the woods in your backyard to play and you come out next to Highway 31? These situations are like what humans would encounter at sea or traveling across vast plains. Can you imagine traveling over the river and through the woods to grandmother's house and ending up in Brazil? Today, we do not really have these problems because of our phones. Being able to punch in our location and our destination allows us to simply follow directions. This map uses signals and satellites to determine our location and lets us know which direction to go. Early explorers and travelers did not have such a luxury. In this presentation, we will discuss early maps and their creators, and longitude and latitude lines and their significance for time zones. Early maps consisted of similar things that we have on maps today. They recorded and consisted of places of interest, small areas, including cities, trade routes, and hunting grounds, geographical landmarks, and typically had no rules to orientation, but which they knew of the earth and their surroundings. Most early maps were looked at as pieces of art. This was a cause of being difficult to make by hand and that they were an item for higher status people. Let us look at some characteristics of early maps and their creators. This Babylonian map dates to around 700 to 500 BC. Although it was accurate in its approximation of the position of places, it serves as an explanation to the Babylonian view of the mythological world. Babylon was placed at the center of the circle, with the circle representing the sea, with other places named in the tablet. 8 regions are portrayed on the map in triangles. These regions have brief descriptions, including beasts and heroes that resided in them. Claudius Ptolemy was an Alexandrian geographer and is credited with a map of the world and 26 regional maps of Europe, Western and Southern Asia, and Northern Africa. This is all included in his book titled Geography, or Geographia. This book contained thousands of references and maps from multiple parts of the world and included longitude and latitude lines and provided information and techniques on drawing maps. Ptolemy was the first person to include longitude and latitude in his maps to ensure that it could be copied with accuracy. However, he did not come up with the system of longitude and latitude. That was created by Marinos of Tyre. He was able to create 2 ways to depict a grid of lines on a map that represent the circles that longitudinal and latitudinal lines create on the globe. Considering humans could not truly calculate longitude accurately until the 18th century, Ptolemy's longitudinal lines were a start. Take a look at his image, his map. Notice that the longitude and latitude lines bend with the shape of the Earth. In the yellow and gold bars on the bottom, top, and right-hand side, there are degree markers for each line. Born in Morocco around 1100 CE, Abu Abdallah, Muhammad, al-Idrisi, al-Qurtubi, al-Hassani, az-Sabti, or simply al-Idrisi, was a geographer who was credited by making more than 70 maps. These maps are in his book, The Excursion of One Who is Eager to Traverse the Regions of the World, and are considered the most accurate maps at the time for 3 centuries. In 1145 CE, al-Idrisi was hired by King Roger II of Sicily. The king hired him to create an updated and more refined world map. Taking on the challenge, al-Idrisi then sent out travelers and geographers to gather information about the landscape of the world. This was the map that was created using the information brought back to al-Idrisi. The map was made to accurately depict the world's geography and terrain. This differed from the maps made in medieval Europe, which focused on imagery and text, which, referred to earlier, were made as a piece of art. I want you, the viewer, to pause the video, to look at the map and try to make sense of any geographical locations you can find. See if you can locate any countries or specific characteristics of the portrayed Earth. If you had trouble, then maybe this will help. Notice anything now? Al-Idrisi created the map with our modern cardinal directions flipped. His depicted north, or up, is our south, and vice versa. So now you should be able to notice, looking at my cursor, that the upper left-hand corner is Europe, bottom left-hand is Northern Africa, and to the right we have Asia. Now let's watch the video that will showcase al-Idrisi's map a bit more. Take note of the book they refer to and look at.
It was a 12th century vision of the world that the world had never seen before. One man's map of everything he knew and had been told of the countries on Earth, engraved onto a massive silver disc and here recreated for the first time.
But nobody's done anything on this sort of scale and detail ever before.
The original disc vanished, thought lost at sea, but the maps created by al-Idrisi survive. The Islamic scholar was commissioned by the ruler of Sicily to map the world, and in 1154 his 69 individual maps were produced.
It's actually got south at the top, so we need to look down like this to try and
Unlike later maps, al-Idrisi's have north on the bottom, but historian Jerry Broughton says his accounts drawn from personal travels and scholars before him are astounding.
Right down here is England. And it's extraordinary because actually that also shows Scotland.
That's Scotland.
Yeah, and this little claw down here would be Cornwall. This is Ireland. And then if you look up, you start to make sense of what you're seeing because it's really Europe upside down. This would be France, and this is North Africa. The islands down here, the Canary Islands. And he probably ends, the westernmost point is Korea. But that's extraordinary, 12th century, and they have some notion of Korea right back to Ireland and England.
Using al-Idrisi's drawn maps and the latest digital technology, an international art team has now made a new silver disc of the world, due to go on display later this week. The level of detail on this silver disc is absolutely extraordinary. You can see all of the Arabic place names that al-Idrisi had engraved. And yet, as you look further up to what would have been south of the equator for al-Idrisi, there is nothing there. And that represents lands yet to be discovered.
What do we think Idrisi would think if he were here and knew that all those hundreds of years after he creates first his maps and then this object of wonder, the same thing is there for people to come and just be delighted by?
Al-Idrisi's maps were followed for hundreds of years. Now they're set to enlighten audiences again. Nina Nanar, News at 10 in Oxford.
Moving on from early maps and their creators, we will now look at the tools used to navigate the Earth and to locate points on a globe. Longitude and latitude are basically Earth's coordinate system. It is a grid to locate any specific point on a sphere. In early maps, places of interest would be measured apart and a ratio would be used to correctly portray them onto a map. This worked on a flat map in a flat world, but with the Earth being round, it does not translate properly onto a flat piece of paper. And although disproportionate maps are still common, this called for a way to represent distance and points on the Earth that accommodated the curve utilizing great circles. A great circle is a circle that is placed in the center of a sphere and is at its greatest length in diameter. Every longitudinal line is half of a great circle, and only one of the latitudinal lines, the equator, is a full great circle. Great circles are used to find the shortest distance between 2 points on a sphere. Therefore, when looking at a 2D map, the shortest distance between 2 points is curved. Here is a video explaining the use of great circles just a bit more.
If you've been watching my other videos, you'll have probably noticed something strange with all my route maps. Take this example of the Southampton to New York route. I always make the ship take a curved path across the ocean. With fuel coming in as one of the biggest expenses, obviously ships normally take the shortest route possible. So why do I use curved lines on these tracks? Well, actually when you're navigating on a global scale, these curved tracks are shorter than a straight line drawn between the origin and destination. The reason for it is to do with the shape of the Earth and the projection of the chart. We all know the shape of the Earth is spherical. To be a little more precise, it's an oblate spheroid, but for simplicity, we'll just assume it's a sphere. If you take 2 points on the equator, it's pretty obvious that the shortest route is to travel straight along the equator itself. As you move further north though, the shortest route starts to bend towards the North Pole. At this scale it may not be immediately obvious, but if we take it to its extreme and we approach the pole, clearly it's shorter to go over the pole itself rather than following around the parallel of latitude. So it may seem like we're taking a strangely curved path, but actually we are following the shortest path on the surface of a sphere. In navigation we call it a great circle track, and it works between any 2 points on the surface of the Earth. Between Southampton and New York, the shortest route is a great circle. The reason it doesn't look like the shortest route when drawn on a chart is all to do with the projection of the chart itself. The most commonly viewed charts are drawn with a Mercator projection. This is just a method of displaying a spherical Earth on a flat sheet of paper while preserving the right angles between parallels of latitude and longitude. We need to do that so that we can easily read compass bearings from the chart. The downside of the Mercator projection is that it stretches the Earth at the poles, which is why Antarctica looks like it's so large when in reality it just covers a small area over the South Pole. As you get towards the pole, it makes more sense to use what we call a polar projection. Parallels of longitude all converge towards the pole, and parallels of latitude appear to curve. It's very hard to navigate on a polar projection because reading courses is so tough. Imagine you are here following your compass due east. Obviously your compass would give you a constant reading of 090 degrees, but your path on the chart would curve, following the parallel of latitude towards the east. But what if we took a great circle track instead? On the polar projection, the great circle track is a straight line. It's the shortest route between 2 points on the curved surface of a sphere. As the parallels of longitude all converge, the great circle track crosses each one at a different angle, indicating that your compass course would need to constantly change. Plotting on the Mercator projection is obviously different. To plot the great circle track, you know that you cross each parallel of longitude at a different angle. The track now appears curved, which explains why I've always drawn ocean passages as curved lines. In reality, we use spherical trigonometry to manually calculate information about the great circle track. We can find the highest point, or the point where you're heading is due east or due west. We can also find the heading that we need to set off at, and we can find the location in which we cross each parallel of longitude. This effectively lets us plot a series of straight lines so that we can use the ship's compass to effectively steer us along a curved track over an ocean. Of course, modern navigational technology can plot the curve accurately, and modern autopilots can steer a ship precisely along that curve. So, next time you are crossing an ocean, you'll understand that even if your track doesn't look straight, you're probably still on the shortest route, and that's because of the shape of the Earth. Hopefully you've enjoyed today's topic. For more videos like this every other Friday,
So now that we know a little bit more about great circles, let's look at latitude. Latitude was created based off the observation that the sun appeared from west to east in relation to the earth. A great circle that cuts the sphere in half horizontally was agreed to be called the equator, with a degree of 0. From this, parallel lines would continue north and south until reaching the poles. These lines would go from 0 to 90 degrees. It only goes up to 90 degrees because creating a line that goes from the center to the equator and a line that goes from the center to a pole, the largest angle that can be made from those two lines is 90 degrees. You can see this here in the bottom right-hand image. Some specific latitudinal lines consist of the tropics, which are two lines opposite the equator at 23.5 degrees north, labeled Cancer, and 23.5 degrees south, labeled Capricorn. During a northern hemisphere winter, the sun at one point will be directly above Capricorn, and for a northern hemisphere summer, the sun at one point will be directly above Cancer. At 66.5 degrees north and 66.5 degrees south are the polar circles. At 90 degrees north and 90 degrees south are the poles. In between the polar circles and the poles can be 24 hours of darkness or 24 hours of light, depending on the season of the hemisphere. This is based on the Earth's positioning and the sun. Since the lines of latitude are not great circles, they have different lengths. The equator is 40,075 kilometers long, and the Antarctic Circle, is 17,662 kilometers long. Now looking at longitude. It was eventually agreed upon that longitude lines would be based on a series of vertical lines around the globe. This allowed the lines to connect the North and South Pole, which created slices, like orange slices. Trying to decide where to put the 0-degree line was difficult, since multiple countries and religions had reasons for numerous locations. A big religious reason was that European maps had Jerusalem as the primary line of longitude. With its status of being home to many early mapmakers, many wanted Alexandria to be the major option. Also, a lot of countries wanted the prime meridian to be placed in their capitals or cities. Some examples include Copenhagen, Madrid, Paris, St. Petersburg, Washington, D.C., and Philadelphia. In 1884, the International Meridian Conference had decided that a line of longitude that ran through the Royal Observatory in Greenwich of the United Kingdom was to be the prime meridian. Following the prime meridian as 0 degrees, The degrees would increase, going east and west, meeting at a shared 180 degrees on the opposite side of the Earth. Now, moving to time zones. Before time zones existed, people would tend to just keep local time. Around the 1890s, for poorer places, church bells or town hall clocks were the main way to consistently tell the time. With the development of long-distance train routes, having an inconsistent schedule due to inconsistent timekeeping caused many problems. Canadian Sir Sandford Fleming, in 1878, proposed having a worldwide way to tell time that was in coordination with each other countries. This time zone proposal was based off the lines of longitude, having 24 time zones for each hour of the day based on intervals of 15 degrees started at the prime meridian and the 180th degree as the end. This, in turn, created the International Date Line, which is the line in which the day is split. Although having agreed upon these time zones, some countries decided to manipulate the time zones to favor geography or having the same general time, disregarding the longitudinal lines of reference. Some main examples of this are China having 5 different time zones, but choosing to only follow one throughout the whole country. Australia and the United States cross several times, but have divided their country into chunks. France and Spain decided to use neighboring time zones of continental Europe. Now let's take a look at a final video explaining time zones and longitudinal lines.
In the old days, each town would keep their own times, with a town clock being set to noon when the sun reached its highest point in the sky. However, by the late 19th century, rail had begun to move people across great distances. Schedules became very confusing, as each stop was based on a different town's time. Thus, a need emerged to standardize time so rail could operate more efficiently. In 1884, delegates from 26 countries met in Washington, D.C. to agree on a prime meridian as a common 0 point for longitude. The result was Greenwich, England, being selected as the international standard for 0 degrees longitude and established the 24 time zones. Today, most countries follow the hourly deviations, though they do not always align with longitudes for reasons such as keeping the entire country in one time zone or altering times at certain times of the year, for example, daylight savings time. Time zones are based on the fact that the Earth moves 15 degrees longitude each hour. Since there are 24 hours in a day, there are 24 standard time zones. Time zones are counted from the prime meridian, which is 0 degrees longitude. Each time zone is counted at 15-degree intervals and extends 7.5 degrees either side of the central meridian. For example, Sydney, Australia, lies in the 150 degrees east central meridian, and the time zone includes all locations between 142.5 degrees east and 157.5 degrees east. Now, I will show you how to calculate time zones. First, determine whether the time zone is in the eastern or western hemisphere. If the time zone is east of the prime meridian, such as Australia, it will be at an earlier time than Greenwich Mean Time, or GMT. If it is west of the prime meridian, such as Canada, it will be a later time. Second, count how many time zones away from Greenwich the location is. For example, Greenland is one time zone to the west of Greenwich, so I will subtract 1 hour from GMT to determine the time there. Oslo in Norway is one time zone to the east of Greenwich, so I will add just 1 hour to the current Greenwich Mean Time. When counting the number of time zones away a location is, count the time zone your location is in, but do not count the time zone that Greenwich is in. For example, I will count for Buenos Aires, Argentina. 1, 2, 3, 4. So, if the time is 4:34 GMT, I will subtract 4 hours to find out the time for Buenos Aires. The time will be 0:34. The international date line is an imaginary line lying 180 degrees in the line of longitude, on the opposite side of the Earth to the prime meridian. This line separates one calendar day from another. The international date line deviates in places to avoid crossing any land. In 1994, Kiribati shifted the date line 2,000 miles east to keep the entire country in the eastern hemisphere. In 2011, Samoa and Tokelau skipped a day and moved westward to be in the eastern hemisphere so they could have the same date as Australia and New Zealand, their main trading partners.
I hope you have learned more about the history of cartography. The development of longitudinal and latitudinal lines was a huge help to the creation of maps, navigation, and keeping time consistent across the globe. Thank you.